So let's continue. So this is the same concept, yeah, same concept. So you can read from the notes. Okay. In the previous example is the explanation. So you can read from the notes, the detailed explanation of that. Same thing, right? So we have designed this already, subtractor tadi. Okay. Now, okay, it's a good thing that we can use the full adder to design or to create the subtractor. But when we use this, right, you can see that this circuit will be always be the subtractor, right? Because you can see the y here is always inverted and always inverted. So this is a subtractor. Okay. This is not good or not practical. Yeah? If we have in the same system, like for example, if you want to have an adder and also subtractor, but we have a different circuit of the adder and subtractor, because we use actually the same um, adder here, the same circuit, just to change this to from invert, from not invert to invert only, right? If you don't have this and we change this to 0, this circuit is actually an adder, right? An adder. And if we put this inverter here, and change this to 1, and we have the subtractor, right? The question is, can we combine both circuit to be what we call a subtractor and adder subtractor circuit, where we can change the function of the circuit to be adder or subtractor depending on maybe the setting. All right, change only some setting. If we want to have an add function, so we can use the same circuit to add. If we want to have a subtract function, then we can use the same circuit to do the same the subtract operation, right? The answer is yes, we can do that by replacing the NOT gate with the XOR gate like this. And this will become what we call the adder subtractor circuit, where this circuit can do add and also sub depending on what is the signal or what is the C in here. If C in equal to 0, or in this case we call a sub signal, if this A sub signal equal to 0, this circuit will perform add. If we change this to 1, this circuit will give you subtract function or subtractor. Only that. So how this is possible? The answer is this. Let's go back to this. Let's look at this. Let's examine this circuit. How this circuit works, right? So this is an XOR gate, okay? And if we have So this is X. And we have XOR gate. So let's draw an XOR. XOR, get the Y. And then we have the A sub or add sub function. And this add sub function is also maybe the input to this Ci. And when we have X, we have CO here. So this is our full adder, of course. This one, yeah. Take this one. Okay. Now this is XOR. Okay, XOR. Okay, now let's have an XOR function and see. Yeah, the truth table, I mean the truth table of the XOR. Okay. This is A sub. Okay, the input to this XOR gate. Okay, we have one is A sub, one is YN. So we have Y here. And let's call this output ke sini small y. Nah, ni, small y. So we will have 0, 0 here, 0, 1, 1, 0, 1, 1. Of course, XOR should be 0, 1, 1, 0. So this is the output of the XOR. Always like this, kan? So tengok ni, ya, if A sub equal to 0, means that A sub equal to 0, this case, and A sub equal to 0. So what is Y? What is Y? So Y will be equal to Y, right? You see, 0, 0, 1, 1, 1. So means that in this case, kalau time this time, this means that Y is equal to Y. So tak ada beza pun. This one and this one. So if this is 0, means that the output here S is equal to S X plus Y. Yeah, because S here is always this plus this. Yeah. So because this is equal to X and this Y is equal to this, so this is adder. All right. So just like this, when this is 0, X is plus 2Y. Tapi kalau this is 1, yeah, if this is 1, what happened? Okay, now when this is 1, okay, 1. 1 means that this. And A sub equal to 1. What happened to Y here? If capital Y, this Y equal to 0, this small y equal to 1. And if this is 1, the small y equal to 0. So it means that y here is equal to y bar, capital Y bar. See? 0 invert jadi bar. 0 go to 1. 1 go to 0. So y bar. Y bar. What happened to S here? S is equal to X plus, ataupun you can say that, capital X here, this X, plus, because this is always plus, Y ni, plus what? Y bar
minus
plus Ci, which is 1. You see this? Y bar plus 1, which is Same thing. So this is subtract already. Okay, so you can see that when we have the XOR gate here, now we can use the same circuit to be adder. Yeah, when we set this equal to 0, this will become an adder. And when we change this to 1, this circuit become a subtractor already. So one circuit, now it can be adder or subtractor depending on only one signal, a sub signal. Right. So this is good in design, you know, because you can save a lot. Yeah, the cost is saved. No need to have two different circuit to do two different function. Yeah, you have only one circuit, but you can do two function, which is very good. So this is called adder subtractor circuit. Okay, and of course you can have a big one. Yeah, this is 4-bit, so you can have a bigger 8-bit, 16-bit, 64-bit, up to you. So same thing. So you can extend the size of the design to a bigger design, depending on what is your requirement. Okay. So now come to what we call the arithmetic overflow. Okay. So what is arithmetic overflow? The answer is this. Is it important? The answer is yes. Okay. Why? Because look at this. Take 4-bit example. Okay. When we have 4-bit number, okay, when we add two number, for example, 6 plus 1, we have 7. Okay. When we represent this in binary, we have 0, 1, 1, 0. Right. When we represent this in binary, we have 0, 0, 0, 1, which is good. When we represent this in binary, we have 0, 1, 1, which is good. All good. All right. This is correct. This is correct. This is correct. What if we have 6 plus 2? The answer is 8. No problem in decimal. We are human. In number system that we have learned so far, this is nothing wrong. This is fine. This is okay. But what in hardware? 4-bit hardware. This is 6. Again, this is okay. Nothing wrong. This is 2. Again, this is nothing wrong. This is 8. Is it wrong? Okay, so we use calculator. When we change to binary, looks like nothing wrong for now. But our system, remember, our system is 4-bit. In this example, 4-bit. If it is 4-bit, when we represent the number into a binary 4-bit, we have 4-bit, right? In sign representation, sign number, we have the first bit to represent the sign, remember, and the rest represent the magnitude value. And of course, in computer, in digital system, we use second complement. But of course, second complement is the same. The first bit or the MSB will represent the sign, where 0 represent positive. 1 represent negative. Now, look at this. This is negative. This is not positive 8, but negative something, right? Because the sign clearly show that this is negative number. Negative number. Okay? And this is positive 2. Is this correct? Because this is positive. This is positive 2. This is positive 5. But this is negative, right? Not positive 8 in 4-bit system. But what is this negative? Negative what? Right? So to know that value, you need to convert back to the second complement. Yeah, because this is now in second complement representation already. So what you need to do is 1, 0, 0, 0. You find the first complement, which is 0, 1, 1, 1. At 1, so you have 0, 0, 0, 1, which is the same number. This is negative 8 in 4-bit, not positive 8. So this is something wrong, because in the computer it's represented as negative 8, not positive 8. So this is called overflow. In digital system, overflow means the number that you want to represent is not fit, yeah, in the system that you use. Because for 4-bit system, the positive number that you can represent is actually starting from the positive, yeah, from 0 to positive 7 for the positive side. 0 we consider positive, and for the negative side, the maximum is minus 8 only. All right. So this one maybe you can go to maybe you can ask ChatGPT, right? The range of binary number, 4-bit binary number, I feel. What is that? The range of 4-bit binary number from, let's say, from negative to positive. So this is unsigned value. We are talking about signed value, see? Yeah. When you ask ChatGPT, you see, the range is from -8 to positive 7. -8 to positive 7. Only, meaning that when you use adder, when you add numbers, if your number is out of range, the result, I mean the result, the sum, the result, x plus y equal to s. This s is, if it is out of range, means that we have an overflow. For example, in this case, exactly because 6 plus 2, the answer is 8, positive 8, right? And based on this positive 8, it is out of range already, so we have the overflow. Okay. So this will give you a problem in design because your system, your number is definitely will be more than 8, right? So that is why we need to have a bigger system. So for example, instead of 4-bit, we can use 5-bit maybe, or 8-bit, right? So for example, it's 8-bit. Our system is 8-bit, 8-bit system. So again, we will use 6 plus 2 as the example. 6 in 8-bit will be, and of course this is 8. 6 in 8-bit will be 0, 0, 0, 0, 0, 1, 1, 0. So this is 6. Number 2 is 0, 0, 0, 0, 0, 0, 1, 0, which is positive 2. Number 8 is 0, 0, 0, 0, 1, 0, 0, 0. And you see the sign. This is positive 6. This is positive 2. This is positive 8. So this is good. All right. No overflow if the system is 8-bit. No overflow. Okay. What is the range for the 8-bit then? The answer is this. So let's use the ChatGPT again. What about 6? Oh no, 8-bit sign. This is the maximum value. Okay, the range is from -1 to 8 to +1 to 7. This is the minimum number that you can use if your system is 8-bit is -2 to 7, -1 to 8, until the biggest one is +1 to 7, right? Why? Because you see, +1 to 7, if you change this to binary number, it is 0, 1, 1, 1, 1, 1. So if you take 1 to 7 plus 1, you have 1 to 8. This 1 to 8 is, if you change to binary, 1 to 8, if you change to binary, you see, this is the value, meaning that 1, 0, 0, 0, 0, 0, 0, 0. Again, you see the sign, negative. So this is wrong, meaning that you cannot represent +1 to 8 using 8-bit out of range. Okay. Now, this is the range. Can we determine the range without asking ChatGPT, right? Because if you have ChatGPT, you have ChatGPT, it is easy to know the range, right? But what if you don't have? Of course, in the exam, right, you don't have. How do you know that? For example, 4-bit, what is the maximum value that you can use? What is the maximum value that you can use? The answer is very easy. Where you need to use this formula. Yeah, we are working in 2 binary system, so, or base 2. So this is how. So to determine the minimum value, of course, the minimum value is the negative side. Then minimum value will be, the formula will be this 2 power of n minus 1, where n is your bit, the size of your system. How many bit is your system? N bit system. And then the maximum value will be positive 2 power of n minus 1 minus 1. Now take an example. If our system is 3 bit, 4 bit just now, 4 bit, right? So if you replace 4 for the n here, so you will have minus 2, 4 minus 1 until 2, 4 minus 1 minus 1. So 4 minus 1 will be 3, 2 power of 3 will be minus 8 here. Till 4 power of 3 is 8 minus 1, you have 7. Right? So minus 8 to 7. Exactly this. Minus 8 to 7. What about this? 16 bit. So again, you change this to not 16, 8, right? 8 bit. Change this to 8. Change this to 8. Now, oops, 8. So you have this 8. So 2 power of 8 minus 1 means that 2 power of 7. So you will have minus 1 to 8 until positive side 2 power of 7, which is 1 to 8, minus 1, which is positive 1 to 7. Exactly. Okay. So you will have this. What if your system is 16 bit, for example? Now let's see. If 16 bit, so you have 16 here, 16 here. So 16 minus 1 is 15. So 2 power of 15. Of course, now I need to use calculator. Okay, 2 power of 15 is 32768. So the minimum will be minus 32768 is the minimum. The maximum will be positive 32767. All right, let's check using ChatGPT. Okay. 16 sine 16 bit. Right? So the range will be from 32768 to positive 32767. Exactly what we have here. Okay. So that is means by overflow. Why is this important? It is important because in digital system, right? Let's say we have an adder like this. This is adder, add, right? A, and our system is 4 bit, for example, 4 bit, small one. And of course, the S here is 4 bit. If A equal to 1, B equal to 1, the answer is 2, should be no problem. Right? But if A equal to 6 and B equal to 2 or 3, as should be equal to 9. But this is problem because we have 4 bit only. Okay, 4 bit at the result. 4 bit only at the result. So number 9 is 1001 in binary. And again, because we reserve MSB as a sign bit, so this is not 9 actually. This is minus something. All right. So this is wrong. So what you need to do is that you need to have an extra space to save the result. So normally in digital system, we will learn in the next chapter, in chapter 4. Okay, the result, yeah, here will be stored in the memory circuit, where we call that as a register memory circuit. Okay, and this memory is, of course, if our system is 4 bit, so it is 4 bit system. So in that case, if the result is big, we cannot store in 4 bit memory. What we need to do is we need to have an extra space where, for example, right, we can save the extra result in the next memory location. So the system, when you have the system, the system need to know that whether the result is out of range or not. Okay, if out of range, so we need maybe extra space to deal with that problem. That is the reason why we need to know whether the result is out of range or not. But this can happen, right? Because 6 plus 3, yeah, we can have all the time. Okay, although our system is big, like 16 bit, the answer of the arithmetic operation might be more than this, right? All the time. So how we deal with that? The answer is by using overflow to indicate that, okay, the result is not fit to, for example, 16 bit. So you need to have a more space, more space to store the result. Okay, so that is how or why this is important. So how we create this hardware to do that, to detect the arithmetic overflow? The answer is not that difficult, where we can take this as the scenario. Okay, for example, we have 7 and 2, x7, y2, means that we add the number. Okay, we take our adder or subtractor, doesn't matter. We have x, we have y, and we will look at the result as, and this is adder, of course, add. And let's take this as an example. If x is equal to 7 and y equal to 2, okay, and we add 7 plus 2, of course, when we get the result 9, this is overflow, right? Because for 4-bit system, the maximum number is 7. So 9 is overflow. So we say that this is overflow already. And let's observe 2 signal, which is C4 and C3. Where is C4 and C3? C4 and C3 is this. in your adder, let's go back to your adder. This is C3, this is C4. C4 should be here. Okay. This is C4 or CO. So this two signal, C3 and C4. Let's observe these two. Meaning that when we look at this 7 plus 2, okay, seven plus 2. 7 is 0, 1, 1, 0. Sorry, 1. 2 is 0, 0, 1, 0, right? Let's add. So you have 1 plus 0, you have 1. C1 will be equal to 0. This is C1. 0 plus 1 plus 0, you have plus 1, you have 0 and 1. This is C2, right? 1 plus 1 plus 0, you have 0. This is C3. 1 plus 0 plus 0, you have 1. And you have 0 carry, right? The carry. This is C4. Okay. So we observe these two. Means that when C4 equal to 0, C3 equal to 1, this normally will give you overflow. Overflow happen, right? The first case, overflow happen because C4 equal to 0, C3 equal to, but let's record that. And what happened if we change the value from plus 7 to y equal to x still remain 7 and y equal to minus 2. Okay, and we do the same operation. And when we do this, we add, we have plus 5. This is no overflow at all, right? So when C4 equal to 1, C3 equal to 1, in this case, no overflow. We change to other possibilities, minus 7, minus 2, minus 7, minus 2, and we have minus 9. This is overflow as well. And this is the C4 and C3, 1, 0. Looks like this is overflow. When we have x equal to minus 7, y equal to 2, we have no overflow, minus 5, no overflow, and C4 and C3 equal to 0, 0, no overflow. So we check for all the possibilities actually, because when you look at this, yeah, we have 7, positive 7, positive 2. We have positive 7, negative 2. We have negative 7, positive 2. We have negative 7, negative 2. So these are the 4 possibilities that this number can be, right? And we add the first possibility, second possibility, third possibility, the fourth possibility, and we observe this C4. And what we found is that when 0, 0, no overflow, 0, 1, overflow, 1, 0, overflow, 1, 1, no overflow. And this is clearly an XOR gate, right? 0, 1, 1, 0 is XOR gate, meaning that when we connect this C3 and C4 to an XOR gate, we can detect the overflow, and we call that overflow as V, right? So any number that you give here, when V equal to 1 means that you have overflow. If V equal to 0 means that you don't have overflow, right? So in data system, to detect overflow is very easy. Just use an XOR gate to this C3 and C4. This is done. What if your circuit is 8-bit? The answer is easy. Same thing. If your circuit is 8-bit, right? If your system is 8-bit, so you will have, so this is x0, x, y0, right? This is ci, this is s0. Let's see, this is the number x6, y6. This is x7, y7. And this will be C7. This will be your C8. So same thing, when you want to detect overflow, you just have these two connect to an XOR gate, and you will have the overflow as well. So you can check this using a Verilog. You can create a Verilog code. You have to do that. So for example, in this case, let's do this to detect overflow, right? To have something like this. Okay. So we will have one signal called V, right? And this V is output, right? And this V is equal to in this case is CO XOR C, in this case, in our case, where is the circuit? CO and C3, right? So it should be C3. And we have V already. And of course, we need to have this also V, and this one, because we have V here, is V, and in this case now we will have V here for this, right, as the output, CO and V. Okay, now let's see the simulation. Let's close this. And of course, we want to demonstrate the hold on. This one is change back to adder, because this one is subtractor. We change to subtractor, right? So we change to adder. This should be the adder already. And then CI this. So now let's see this. This 6 plus 1 is 7. Now x equal to 7. 7 plus 1 should be 8. And we should have overflow here, right? In this one. So it's good. Now let's okay, and let me run this. Okay, simulate the design and see what happened. Okay, the class today will be a little bit long because I want to finish at what you should know before you go to the test, right? So it will finish at before 5. Okay. So one more thing that we need to learn today is the comparator. But don't worry, comparator is just an extension to the adder and subtractor that we have just learned, meaning that we will use the same circuit. We will see after this how the subtractor is built, right? But let's see this thing first. Okay, now we have the overflow. Here, what we can see is now decimal, right? You see, when we add 5 plus 2, number 7, this is no overflow because number 7 is uh, within the range. Doesn't matter. 6 plus 1 is still 7. This is still 7. So within the range. But you see this 7 plus 1. This is minus 8. Okay, if you can see this is minus 8. This is wrong, you see, because x7, y1, 7 plus 1 should be 8, but you have minus 8. But because you see the overflow indicate that, okay, this is overflow, b equal to 1, meaning that the result is not fit. And this is overflow. Okay. The use of that overflow is demonstrated here. And this is important, okay? Especially in the arithmetic circuit, like the CPU, in our CPU, in our everything today. We have the CPU inside, right? And of course, CPU will need to have the arithmetic circuit inside, and this overflow is very important. Okay, so I hope that this is clear for you to understand why we need overflow and how overflow is detected in digital system. What is overflow is of course important. Yeah, you need to know what is overflow and also how it is detected in digital system. And you can see that this is not that difficult. We just add this thing. Okay, add this to your design, and you will have the overflow already. Okay, now how to compare number. Comparator is very important in computer, in data system, because we compare number all the time. Okay, for example, when you write a C program, when you write the syntax, for example, if you say if, means that you compare something. Okay, now let's look at this. In computer programming, when you say if a equal to 0, means that you compare whether a is equal to 0 or not. Or when you write if a equal to b, means that you compare something, right? You compare a to b. Or maybe you say that say this: if a equal to, not equal, if a greater than b, if a less than b, means that you compare, right? Compare something. How did the system comparing numbers? Like for example, if we have a equal to 5, b equal to 6, how do we know that 6 is greater than 5 or b is greater than b than a? The answer is by using comparator. Now, what is the idea? How to compare number? The idea is easy. To compare number, we use subtractor. We subtract number and we know that For example, if you take A minus B, if the result equal to 0, our conclusion is that A equal to B, right? If you take A minus B and the answer is greater than 0, means that the answer is positive. So this means A is greater than B, right? If we take A minus B, but the answer is less than 0 or negative, this means A less than B, right? Because we get negative value. So this is how we compare number, right? It's easy. So how to check whether A minus B equal to 0? The answer is this. If S equal to 0, right? So we have an look at this 4-bit adder. Subtractor, not adder, right? But of course, our subtractor, we use the full adder, of course. So how to know that the answer is 0? I mean, if you x3, y3, x2, y2, x1, y1, x0, y0, and you subtract x minus y, how do you know that the result is 0? S equal to 0 means that the output here equal to 0, equal to 0, equal to 0, equal to 0, right? That means x equal to y. So in data system, how to detect this? The answer is we create a truth table, right? Truth table. So the truth table is this. We have S, this is S3, right? S3, S2, S1, S0. And we have a signal called Z. Z represent 0, okay, called Z. And Z equal to 1. Z equal to 1 when A minus B equal to 0. Or in this case, it's not AB. X minus Y equal to 0. And Z will be always 0 when x minus y not equal to 0. In other words, s is not equal to 0. So when all 0, z equal to 1, right? Based on this specification, z equal to 1 when x minus y equal to 0. X minus y equal to 0 means that all 0, z equal to 1. When x minus y not equal to 0, z equal to 0. What is meant by x minus y not equal to 0? Means that any other number, for example, this is 0,0,0,1 or 0,0,1,0 or any other number that is not all 0, right? Meaning that 0,0,0,1 z equal to 0, 0,0,1,0 z equal to 0, any other numbers from 0,0,0,1 to 1,1,1,1, z should be always equal to 0. Meaning that z equal to 1 only if all s here equal to 0, stating that x minus y equal to 0. That's it. And this is easy. What is this gate? Of course, this is a NOR gate, right? NOR gate. To detect whether x minus y equal to 0 or not. We can use NOR gate like this. Z. If this is 0, 0, 0, 0, z equal to 1. Otherwise, z will always 0. Means that if z equal to 1, x and y is equal. X equal to y. That's easy to check 0. So z equal to 1 is the result equal to 0, meaning that if z equal to 1, x equal to y, right? That's it. What or how to check whether x greater than y? X greater than y means that the result is positive, right? How to check whether the result is positive? To check whether the result is positive is check the S3, the MSB, because the MSB is the sign bit, right? If sign equal to 0 means that the result is positive. And when the result is positive, x must be greater than y. And if n equal to 1 means that the result is negative. When the result is negative, means that x is less than y. That's it. So this is called a comparator to compare whether x is equal to y or not, or x is less than y, or x is greater than y. So for example, if x equal to 3, y equal to 3. So when we have this circuit, this is subtractor, right? We have learned this already, subtractor. So when x equal to y, x equal to 3, y equal to 3, so we will have s3 equal to 0, this equal to 0, this equal to 0, this equal to 0. When this all equal to 0 means z equal to 1. When z equal to 1, we will know exactly that x is actually equal to y. That's it. But if z equal to 0 means that x is not equal to y. When x is not equal to y, there will be two possibilities, whether x greater than y or x less than y. Now to know whether x greater than y or not, check this. Okay, so if n here, n which is connected to S3, n is equal to 1, means that the result is negative. When negative, x is less than y. If the result is positive, then x is greater than y. Okay, so this is called comparator. Now let's see the demonstration here. All right, so we need a subtractor. So I will change this to subtractor again, and I will need to add one signal called n, one signal called z. All right, and this n and z will be the output. V I have already, and I will create n. Easy to create n, where n is equal to S3, right? S3, right? For n. What about z? Z equal to x x this is no gate, right? No or not no gate. So what we can do is not as 3 or as 2 or as 1 or as 0, right? So this is the NOR gate using the data flow modeling. So you can use structural modeling as well, right, to create a NOR gate. But in this case, I will use the structural data flow modeling. Easy. Okay, not S3 or S2 or S1 or S0 exactly, because this is a NOR OR gate with a NOT function, right? So I create this already, and of course, in the attachment, I will need to change this to 1 to be a subtractor. Okay, and also I need to have a N and Z. N and Z. All right. So I have N and Z. Is it the same with this one? B and Z, B and Z, S, B and Z. Okay, that's correct. Now let's see this. Let's have the same. This should be the same. This is X greater than Y, right? Let's have one that X is less than Y. So for example, we have X equal to 2 and Y equal to 5. Okay, so this is the case when X is less than Y. This is the case where X greater than Y, X greater than Y, X greater than Y. This is X equal to Y. Let's have one here. It's better, right? Or maybe 0, 0, and we have another one. X equal to, or maybe we change only Y, or just X equal to 5. Y now equal to 5, so it's the same. Save. Okay, so we don't have any error. Run the simulation. So I need to close this first. So remember that if you want to have a new simulation, you need to close the previous simulation. If you use the same project, but if you have a different project, you can you can have many model sim open at the same time, right? But this is the same project, so you need to close all the model sim for this project and run again. If not, you will get the error when you want to run the simulation. Okay, it's not finished yet. We finished now. Okay, we have all the signal that we want. So let's change this right again to decimal. Right. So see here, if x equal to 0, y equal to 0, x and y is the same. So we have z equal to 1, meaning that x and y is equal. Right. Now 5 and 2, x is greater than y now. So you see z equal to 0, and we need to check n, and n equal to 0. When n equal to 0 means that the result is positive. When the result is positive, then we know that x is greater than y. And this one is also the same, x is greater than y, x is greater than y, but now x is less than y. And you can see that 2 minus 5 is minus 3 is correct, right? It is correct. And x is now less than y. You can see that this is z equal to 0 means that x is not equal to y, but x is less than y because n equal to 1. N equal to 1 means the result is negative. When the result is negative means that x is less than y. And here is x equal to 5, y equal to 5 means that x equal to y. So you can see that when x equal to y, z equal to 1. This indicates that x is equal to y, right? So this is called a comparator. In other words, we can create a comparator using a subtractor, right? This is subtractor. Create the z to see whether the input x and y is equal or not. Check using the z signal. And if you want to see whether x is greater than y, you check this. And or if x is less than y, also you check n. If n negative means that x less than y. If n positive means that x is greater than y. So that is the comparator. So up until this, today, is enough, is sufficient for you to sit for the test, to go to the test, because the test will be from chapter 1 until chapter 3 until the comparator arithmetic circuit. Multiplier is a lot bigger, so you can try to learn this on your own, okay? And maybe after the break, we will look at a little bit more about the more advanced modeling style that can be used to create the adder subtractor in a more easier way, all right? And also the comparator in a more easier way, okay? And we will look at how to create an array construct, to create a repetitive circuit in a very simple way, okay? Create a bigger adder, for example. Today we will learn how to create an adder, right? So to have a bigger adder, we need to do this, right? This is 4-bit. If you want to have 8-bit, so you need to have 8 more lines. And even if your adder is 32-bit, right? And today we have a 64-bit adder in our computer, right? So to do this way is not that practical anymore. So we can have a more practical way to do that, to using the array construct. By using something like this, we can have a much bigger adder with a very compact code. All right, that's array construct. Okay, so ini kita tengok next week lah, next week. And then you can try the tutorial. Tutorial ada banyak tu, boleh try. Dan next week sebelum test tu, you boleh tanya saya berkenaan tutorial ni. Okay, buat tutorial daripada chapter 1, chapter 2, chapter 3. Do the tutorial. Practice. Maybe saya share the past year question juga in order. and post your test question so that you can try to do and have some idea about the test. Okay, so I think that's it for today. Other any question?